Yeah, well,
okay.
no, it's like my.
Let me just say hello to anyone who's listening, and welcome to the Sparks first demo recording session. Today, this is our first one, so we don't have many demos yet, but this is today we're going to have Peter, and he's going to be doing a quick demo for us. So please, Peter, let us know what the demo is and take it away.
Yes, so this is a demo of something that has been worked on for like almost 2 months. So it's not, it's not exactly a proof of concept. What we're going to do is we're basically going to cold start a Lotus backed by the Blockstore that has been, slowly coming together. And in fact, like I wasn't expecting this to be recorded, so probably nothing will work. But basically, what I have here is I have a box that has been like completely cleared of all caches, and I have a Postgres which is like completely stopped. I stopped this like 10 minutes ago or something like that. So let's see what is going to happen to basically bring everything up from absolutely nothing. And I actually don't know how well this will work, but it should be within within correct parameters. So yeah, there we go. So now we have a Postgres running, and you have a thing here that runs every second and basically tells you like, this is what this node has seen epochs wise and tips. When was it seeing particular tip sets at what time and so on and so forth. So basically this will show you that in real time you can actually see everything happening with it. So don't like mind that this machine has a ton of memory. It's my dev machine, like generally this entire thing can work with like 60 gigs of RAM or something like that. So we're just going to start this Lotus and we're going to see what happens. So what it does right away is it basically, so Postgres is slow as a general database when you go like the way we use block stores normally, and you just go one block at a time. What this has, however, is because everything is transaction based and so on and so forth, I can, within every tip set, I can keep a record of like, in order to complete this tip set, those are all the thousands or maybe tens of thousands of blocks that I had to touch. I record that. Then I record this for next tip set and so on and so forth, and I keep a tally of these things. And then when I start stuff, it knows what are the last, I believe I said right now, 3,000 epochs of blocks that I have seen. And I'm just going to load all of them in bulk together. Now, normally this is way quicker than that, but for the sake of the demo, I want to basically do a complete cold start to see exactly how this is going to work. So by now, this should have set like listing that many and that many blocks, took like 10 seconds or something like this. But the important part is that in the meantime, Lotus is still working. It's basically still doing its slow thing, like one at a time and so on and so forth. But in the background, we'll now see that we start 25 preloading threads, and we're going to read 35 million blocks out of the block store at once. It took us like 71 seconds to figure out what we're going to load. And you can see that, it's going to town. It is reading from disk. It is, putting them in RAM and so on and so forth. And you can see Lotus growing a little bit. Most of this memory is actually the in-memory cache of all these blocks. And in fact, in a moment, once this is all loaded, it takes about 200 seconds, it will tell us like exactly how much it had to load. And from this point on, this entire thing is essentially like self-sustaining, because almost everything that needs to touch for any kind of state validation is already in memory, and whatever it writes to the database, it is right through and so on and so forth. So I'm going to switch to the other screen for a moment. Like, this is not going to scroll away because it looks exactly for this logs here. Let me see where it is. Okay, so yeah. So this is where I stopped it at 514.859. And right now we're at 881. So it has been out for like, what's that, 30 blocks or something like that. And this is me hitting the API. So the API actually works. It does respond to commands and so on and so forth. It's just taking quite some time for it to get to the actual chain validation, because again, this thing is still ongoing, and it is taking that long because I dumped all the caches. So if this database was already running and it had like most of the stuff in memory, by now everything would have been already spinning and so on and so forth. But it's it's good to see what's the worst case scenarios. So in the meantime, let's go here. And by the way, here you see that we already like jumped one. It took us like some time, and this will like keep going up. So a couple of interesting things about this Blockstore, and this basically the part that is really not specific to Filecoin in any way, shape, or form. It's just that the Filecoin is the largest Blockstore by far that we have compared to anything else. For example, Cluster, while it is larger data size wise, it is about 20 times smaller than the current chain if you put it all, if you put the entire chain with all the states and so on and so forth. So we're currently at about 2.8 billions of blocks, and Cluster is like some low amount of millions. So the interesting part about this particular, and let me show you what does this mean for, so while planning all this, I had to kind of figure out, like, can I actually do that in Postgres? Like, a specific like design constraint here was that people can run this themselves. Like, it doesn't have to be like, hosted service or anything like this. And if I were to, like, currently I don't have like all the blocks in there because again, still in dev, but if I put every single block that we have, like for all the states, for everything, I get to about 5% of my capacity that a Postgres can store before it starts running out of like different OIDs and stuff like that, which basically gives us about 5 to 7 years, depends on how exactly the chain grows. So this thing is quite durable. And the next thing I want to show you is actually how the specific table is organized, because this is the interesting part. So it's actually not that much stuff going on in there. We have a block ordinal, which is an auto-incrementing 64-bit integer. I'll come back to it in a moment. We have a subdiag max depth. We'll come to it in a moment. The size of the block, how the block is encoded, the actual content, the CID, and linked ordinals. Now, the CID is obvious, except this block store, unlike pretty much everything else that we use, stores complete CIDs. So it doesn't go just by multi-hash, but you can store like the same block, like for example, as CBOR and DAG CBOR, and it will be 2 different entries. And moreover, it allows, the main reason I do this is it allows me to store identity CIDs, which basically allows me to have the entire DAG in one place. Why is this important? Because I have a thing called linked ordinals, which basically, whenever I put a block in, I actually parse it for links. And I record the block ordinals of every CID that is seen in these links in this array. What this basically gives me is I can traverse a DAG entirely in the database without ever like touching Go or anything like that. And this is super important for any kind of, like you can actually do preloads of small subtrees. You can say like, don't give me just this CID whenever I ask for it, but give me this CID and then like 3 levels down or something like that. And it's extraordinarily fast to do in Postgres. And moreover, you can like go ahead and do an entire chain export directly from this, because if you know which tables and which CIDs you're interested in, you can just say like start from the CID and then just traverse all its links, which are already in here. So this will take care of the chain exports, which are extremely slow right now and very resource consuming. Here I probably can bring them down to 5 minutes for a full export or something like that. And why this is interesting for anybody else in IPFS land is because if you have that, and then you walk through and layer by layer figure out what is your depth for each individual DAG, you can then basically go through the entire set and go like, okay, for stuff that we already know what is the max depth, which means that we know the entire underlying DAG, we can see which, we have a reverse index where we can see which blocks are not referenced by any of the routes that we're interested in, and we just delete this top layer. And then we repeat this again, delete this next layer, and we have basically free GC, more or less. That is entirely index driven. It doesn't lock anything. It's just GC. I don't do any of that right now because in Filecoin I actually need every single block that I see. But this is one way out of the GC dilemma. And yeah, in the meantime, this thing is already working. It is at to resize things a little bit. So we are already at 872, so we're halfway there. It started from about 20 seconds per block. It is now down to 18. When everything is warm and fuzzy, it will actually be at about 4 seconds per block validation. So it's extraordinarily fast. In fact, here we go. We successfully primed the cache. It took us from cold start entirely 209 seconds at 77 megabytes per second. If things were warm, this would be about 150. And yeah. And the other thing that you can do now, I unfortunately don't have this ready for the demo, but you could spin up another Lotus off of that directly, of the same block store, writing literally in the same tables because everything is content rest. They know how to lock each other, how to not get into conflicts and stuff like that. And each individual each individual instance has its own namespace. And in there we have several tables, which are basically the access log, which is not Filecoin specific. It can be like for, access log and recent access, where basically you can simply instruct, config parameters, either save that many recent blocks and just purge the table from time to time when they become too old, or literally for every individual block access, just store it down to a microsecond resolution so that you can later come back and do frequency analysis on like, oh, I'm like taking these blocks, like I'm accessing them all the time, and I should like fix my code or something like that. So this was another thing for the actors team were interested in that. And tipsets visited is the part that basically records for each individual instance what did it see when it was syncing the chain. And lastly, the thing that is missing here and why it's not kind of like considered finished the actual library. When we go through tipsets, we can actually record what is orphaned as Lotus itself goes through. So we can have a list of orphans as opposed to the list of what's considered the main chain right now. And then all the transactions that we like record, all the messages, all the stuff from the storage market actor and so on and so forth, if we tag it with a state, then we can simply exclusive join it with the list of orphans, and we have an always up-to-date real-time view of what is actually happening on the network. Plus, we can examine like what Nicola wanted. We can examine how the how the orphanage works and so on and so forth. And yeah, this is pretty much it. And that is what my proposal is like, based on that. Once the big database with all the blocks and everything is available and is streamable as a replica, starting off of that with a much smaller like pre-caching and with a much smaller context of what you actually need should be taking like within 5 minutes or so. I mean, as you saw, as I was demonstrating, even with cold start and everything, we actually did start syncing within 10 minutes. So yeah, that's all I have. I guess any questions?
That's super rad. I'm totally blown away by how cool that is.
Yeah, really cool. This is neat.
Volker had a question.
Yeah. So I'm interested in the access log. So does it mean that it could be used to kind of replay access patterns on the data? Mm-hmm. So because like so the figure is when I was building my index, I still wanted like what is the access pattern actually, and like it would be super useful if you could just like replay actual access patterns, because this is what you want.
Check it out. So you have the block ordinal. Now, I actually didn't talk about the block ordinal. The reason I don't use CIDs everywhere, because the block ordinal is 8 bytes and a CID is like 38 bytes. If I like reference everything by CID, my thing will be too big. So we have the block ordinal, which is a reference to the CID table. Access type is I do not remember my access types for a moment. How did I name them? Access. The access types are, I track the put, the get, that has the size, and I have an OR on them, whether it was already seen in the cache. So even if it is in the cache, I still keep a number that I did hit it in the cache, and I still record it. So you can replay the thing that you asked for. And then how many times within this time? The actual time is rounded up to my millisecond, So 1,000 times a second is my resolution. And if I supply it, the epoch in which this happened and which tipset this happened on. And when we switch to the next tipset, we flush it again. So yes, you can totally replay this.
Cool, because, and then you can, as you said, you also store like puts and gets. You could even get, for example, information about like what's the ratio between puts and gets. Yep. Because this is also not clear to me. Like, I just don't know. And I'm not sure if anyone knows.
Yeah, well, that's what this is for, yes.
Yeah, cool. Yeah.
I have a question. So is this data store suitable for miners, or are you thinking that it's only really useful for PL internal things, or for
you can totally run a node off of that. You can import a snapshot and just run with that. The actual change to Lotus itself is not very large at all. Actually, it's more complex, the tracking of the tipset states and stuff like that, because this is additional. But the actual Blockstore part is literally just like Hannah's work. Change this Blockstore to this other Blockstore, and that's it. Yes, yeah, go ahead.
What's the difference in is it significantly better right now to use this store instead of what's currently there?
Yeah. So the reason it is essentially significantly better is Postgres is extremely economical. Like, this is the amount of memory it takes for each individual worker. Well, it moves around, but you can see 300 megs. So it's like nothing. And the most of Lotus right now is taken by, where did it go? Most of Lotus is taken by the cache. So I actually run it with 32 gigs of cache because I store like 3,000 chipsets back, which is way too much. I could bring it down. And so if you were to run the actual Badger thing, it essentially requires the entire, for it to perform well, it requires the entire, the entire index more or less to be in memory. And the index is really large right now. It's like 380 gigs or something like that. And you either see that or you see like crazy trashing on the hard drive. And as you can see here, like the access patterns are not like very heavy at all. Like this is disk reads, right? It's, I mean, yes, it's doing things, but it's not like, not how normally it looks when a batch is running. So yes, it would be beneficial for folks to switch to this. The downside is that you need to have a Postgres running, which, you know, it's not self-contained, and
yeah, I guess that was kind of one of my questions. But then aren't most miners like cloning the repo and building from source anyway, with a whole bunch of dependencies that they have to install to do that? Like that doesn't feel to me as like it's a, you know, huge hurdle. But that's rad. That's really cool.
Yep. And yeah, so that's it. And yeah, if our thing gets selected, you know, we'll actually publish an actual thing on top of that. If not, then, you know, then it will just be used for the analytics part, because Sentinel is also very interested in seeing that. And yeah, one thing that I need to address, I said that this will come down to like 4 seconds. I have turned on the synchronous parsing of blocks. So whenever a block comes in, it actually needs to look at it and move its links around and stuff like this. So basically the linkage is always up to date. So that's why it takes longer per chipset. And that's fine, you know, because if when you're caught up, it's okay. But you can shut this off, then it will go down to like 4 seconds per chipset. And then there's a background process you can start that will basically fill things in for you. So yeah, that's, again, under development, I forgot I had this turned off. But yeah.
Amazing. And to boot, your demo totally worked, and the demo gods were...
I know, right? Yeah.
All right, I'll stop recording now, but thanks very much. Let's